Too far away from my mouth. Someone just put their hand up. Warn me. Okay. So yeah, I'm going to talk about this work that we've been doing on something we call RichWasm, which is WebAssembly with a rich type system. And the goal here is essentially what the subtitle says, bringing safe, fine-grained, shared memory interop to WebAssembly. All right, so how we got started on this was, there are many different languages that compile to WebAssembly right now. Many of them are type-safe languages. And my group does a lot of work on studying interoperability between different source languages. And in particular, we'd like to have a platform for studying safe interop between languages like, let's say, OCaml and Rust, which are very different type systems. So can we use WebAssembly as a platform where we can do, provide better support for this? So the goal is to support safe and flexible interop between languages with very different type systems. But the problem with Wasm as it exists is that memory sharing between Wasm modules is currently all or nothing. I'll say a little bit more about this in a second. And the current interop proposals, Luke talked about the component model this morning, very rightly, are focusing on lightweight isolation and therefore focus on shared nothing interoperability. So what we'd like to do is actually, when you know that safety is not an issue, we'd like to be able to safely share memory. So that's the goal of our work. So fine-grained memory sharing with strong safety guarantees. So let's look at sharing memory in WebAssembly right now. So right now, WebAssembly has every single module has its own memory, and it's all private unless you export it to another module. So module B here can import this memory, and now it does have access to module A's memory. Everything is good, except maybe not so good, because module B can just go ahead and do pointer arithmetic, which means that every single thing in module A's memory, now that it's been imported into B, is accessible to B. So with pointer arithmetic, you can just read everything. Nothing is private anymore. So there is a proposal, the WebAssembly multiple memories proposal, that seeks to provide sort of a solution to this. If module A knows that it would like to share some stuff and keep other stuff private, it can keep put all of the data that's private in memory 1 and all of the data that's public that it wants to export to module B or other modules in memory 2. And then module B only imports the second memory. But again, this is kind of a coarse-grained sharing approach, right? Because module B can still do pointer arithmetic and read anywhere in the second memory, which you can say is okay because it's public. But there is a problem still because source programs have to be aware of the distinction between private and public so that the compiler can appropriately make the right choice. What stuff do I put in the private memory? What stuff do I put in the public memory, right? You have to sort of a priori make that choice. And in general, I was talking about safe interoperability between source languages. So, this proposal doesn't help us with enforcing abstractions that might exist in different source languages, such as ownership, for instance. So it doesn't really give you the memory safety guarantees you might be looking for with shared memory interop. And another challenge that we wanted to address is supporting sharing memory between languages that have very different memory management strategies. I've been talking about interop for many different years, and almost always someone will bring up this issue like, what about if I have a language with a garbage collected memory and another language which manually manages its memory, right? Like, how do you handle these things? So that was something that we wanted to be able to handle going in. Okay, so our goal, safe shared memory interop between high-level languages compiled to Wasm, even if they have different memory management strategies. And in particular, we've been thinking about ML and Rust, though we can't fully do Rust yet. I'll just say that right now. Let's take a look at what happens when a language like OCaml and Rust currently interoperate, right? You can break memory safety guarantees, and I just want to use this example to show you how. On the left, I have an OCaml program. On the right, I have a Rust program. The Rust program is going to use some of these functions that OCaml provides. So let's take a look. What's happening? At the top here, I'm just creating a mutable reference to a function. The function takes a unit, returns a reference to an integer. Then I have this increment function. It takes a reference to an integer right there, but then it stashes it away in that function that's stored in the mutable reference f, and then it increments the reference. So it's doing this extra stashing before incrementing. The name increment just indicates that it's doing the last line. And then there's this read again function, which basically goes ahead and reads the function out of that reference f, calls it, and then returns the location that we stashed into the function. Reads the contents of that location. So now let's go over to the Rust side. Here, Rust is allocating a mutable reference. Then we go ahead and we increment that using the ML increment function, which means that the reference got stashed, right? Rust mutable reference just got stashed in OCaml code. And then, we print, etc. But when we get down to the end of this scope, the Rust compiler thinks that it's perfectly OK to deallocate that Rust reference. So it deallocates X. But then after the end of that scope, if we read again, this is going to be a problem because we're reading a location that is no longer there, right? So that's going to cause our code to crash. Okay, so this is the kind of thing, right? Because OCaml doesn't understand Rust's notion of ownership, it can stash away a reference which should not be allowed if you really want safe interop between languages like this. Okay, so what we've done is we've developed this richly typed WebAssembly that includes something called capability types to capture memory ownership and memory access. And I'll explain what that means in a second. Let me just sort of say something about the overall picture or architecture that we're after. We're thinking of, type-preserving compilers from languages like ML, and we, as I said a few minutes ago, we don't actually do Rust yet. We do this core calculus called L-cubed or L3, which has ownership types, but it doesn't have borrowing. So that's the sense in which we can sort of do a subset of Rust, because we can do ownership but not borrowing. Okay, so we have type-preserving compilers from ML and L3 down to RichWasm. And then from there, we compile down to WebAssembly. So we erase types, et cetera, and just compile down to standard WebAssembly. The way that we're sort of achieving our goals, if you will, is we have a very simple FFI that allows some additional, annotations to do interop between ML and L3. But then the goal is that it's after you build your type-preserving compilers, it's type checking at the RichWasm level. When you link the two modules together, that's where you catch the errors. That's where you catch the type unsafety or type safety violations, such as the one that I showed you before. And I'll close the loop at the end and show you, give you a slight sense of how we do that. So let me dive into the design of RichWasm. Basically, let's start by talking about the memory model. So we have two global memories. They're shared across all modules. This is the RichWasm memory model. It's different from the Wasm memory model. So we have this memory that we call unrestricted memory. This is the garbage collected memory. Okay? And then we have a memory that we call linear memory. This is the memory where we will put any data structures that are manually managed. Okay? Now, I know that linear memory in Wasm means flat memory, right? So that's an unfortunate thing, but whenever I say linear, I'm using it in the sense of linear types or unique types so that you have only one pointer to something in the program. Okay, little unfortunate thing. We keep thinking about whether we should rename it. Okay, so both of these memories are maps from locations to values, okay? They're not byte arrays like WebAssembly has. So it's a higher level memory model in that sense. And only pointers to the beginning of data structures are valid. Okay. Now, what is a pointer? A pointer in RichWasm is going to be a pair of an address and a sort of qualifier or annotation that specifies, does this address live in the GSeed memory or in the manually managed memory? So that the unrestricted means this lives in the GSeed memory and this lives in the manually managed memory. Okay, let's talk about types. The most interesting types in RichWasm, and these are actually pre-types, I'll explain in a second. We separate out this type for pointers. So this is the type of a pointer to a location L, and a capability to actually use or reference that location. So the capability, this type says that I have a capability or permission to use location L in either with a read access or with read-write access. We can choose either one. And it says that the shape of the data, the content stored at location L, is described by this type psi. Greek letters, Okay. All right. So then you saw the letter psi, right? That describes the shape of data that lives in memory. What we have is, we have structured data in RichWasm. We can have variants, structs, arrays, existential packages. And you'll notice something strange here. This is a struct with a bunch of fields tau, but for every single field, we also need to keep track of the size. Similarly, for an existential package, we keep a bound. We say, oh, alpha is a pretype. That's going to be some data somewhere. But what is the upper bound on the size of that type? And we need this so that we can ensure safe, strong updates of the fields of a struct and for local variables. And I'll talk about that a little bit more later. But basically, this is a low-level type system. It's talking about memory layout. It must track sizes because it's allowing strong updates. You can't go, update of some location in memory if you don't have enough space there. You can't put a value that's bigger than what will fit there. And the type system is keeping track of that. Okay. So what are the types? Again, P is for pretypes. I'll put a qualifier on those in a second. But we basically have unit numeric types, tuples. We have this interesting type which says there exists a location row. Row is just a location variable, such that I have a package type tau. We have the capability types that I showed you before. And the pointers that I showed you before. But we also have these references, and basically all that a reference is it pairs up or packages up together the capability for a location with a pointer to the location. So just think of the combination of those two things as a thing that we call a ref. Okay. We also have this ownership, own L type. And this is useful because often we want to be able to take a read-write capability, split it up into a read capability, but then we need to keep its ownership capability somewhere so that we can later combine them. So we can go in both directions. We can go from here to the pair of these two things, and later we can combine them and go back to that. Okay, now I've been calling these pretypes because all of these data types, if you will, come annotated with a qualifier which says, is this data to be treated in an unrestricted fashion, which means you can make unlimited numbers of copies, or should it be treated linearly? And we also have qualifier polymorphism. That's why I have this qualifier variable delta in order to support that. We're going to have a lot of different kinds of polymorphism. Brace yourself. Okay, we're here. So we have this code ref type, which is just a code pointer, to some function whose type is C. And function types, if you ignore the for all kappa, right, this is just a regular function type, right? I take a bunch of things on the stack, a bunch of tau 1s on the stack, and the function produces a bunch of tau 2s on the stack. But we have polymorphism over a bunch of different kinds of things. So I've already mentioned qualifier polymorphism, but we also need to support location polymorphism, size polymorphism, qualifier polymorphism we've already talked about, and then pretype polymorphism over alphas. And you can see that I don't just have rho, sigma, delta, alpha here. I have a bunch of constraints on these things, which are very useful in the type system. In the case of sizes, we end up in the type system wanting to collect lower bounds and upper bounds on the sizes. And we can have a bunch of them kind of coming from different parts of the type system. We have, again, lower and upper bounds on qualifiers. And just to be very clear here, our qualifier ordering says that unrestricted is less than linear, so in case I end up sort of referring to that. And then we have this size bound on a pretype. Why do we need that? Well, if I instantiate an alpha, with something, let's say a struct of a certain size, it better be smaller than whatever this size bound is. Because in my function body, I'm going to be relying on the size bound to make sure that if I use that alpha and plop it into somewhere in memory, that memory size is big enough. Okay? So basically, this kind of function bound is going to appear here, right? this kind of pre-type bound is going to appear in the function signatures, and we need to know that when you instantiate the function, you're doing it with a value that's not too big. Yes?
So that's where upper bounds on size come from. Where do the lower bounds come from?
The lower bounds are often collected in other places. I think I have another example that I can show you.
If I want to use a type only behind a pointer or something, can I also just say don't care about the size?
Could you repeat the question?
If I want to use something only behind a pointer, then can I say that I don't care about the size? Yes, you don't always need to care about the size. So for example, if the function body, yeah, so for instance, if you're instantiating a function with an alpha and it's a box type, yeah, you don't care about what it's pointing to, right?
The grammar allows me to have an alpha with all the size.
Yes. Okay. All right, so then once we have, this set of features, ultimately what we're after is if you have module A and it has a pointer to this location 1, which is an unrestricted reference with read-write capability to an array of I32s, location 1. Since this is an unrestricted memory, we want it to be the case that we can make a copy of this and give it to module B, and now module B will also be able to point to it. This sort of thing should be allowed, and I'll go through an example later and we'll get a flavor of it. Conversely, if module A is pointing to something in linear memory, again, it's at location 1, it's an array, but it's linear this time, then if we want module A to sort of share this linear reference with module B, then it has to give it up itself, right? Because it's in linear memory. You can only have one pointer to it from anywhere in the program at any point in time. So that means this has to go away. A has to give it up, only then can it sort of pass it to B. That's the rule. Okay, let's talk about garbage collection. So basically what we've done in RichWasm is we've axiomatized all of our rules of garbage collection. The way that, we've done the formalism, we've axiomatized the various rules. So let me give you a flavor of what we can and cannot do. So we do allow unrestricted memory to point to linear memory and vice versa. The garbage collector will reclaim any unrestricted or GC'd memory by following all the unrestricted references from the roots. Okay? Now, there's a tiny subtlety. And this is not a big deal, but I want to explain it anyway. There's this question of, can we store capabilities in the heap? Okay? And you'd say, okay, why not? But the tricky part is that, let's say L1 is a root, and it's pointing to something in the heap, and we want to go collect it. Let's say we're the garbage collector, we want to go collect it. The problem is that not problem, maybe good thing is, that when we compile RichWasm to Wasm, we erase all the capability types. So anything that's only needed for static checking, for checking type safety, is going to be erased. Okay, so capabilities are going to be erased, pointers are not. Right? Pointers are actual addresses. Something of type PTRL is an actual address, and that address will not get erased, but anything that's a capability is just a static thing, it's ghost state, and that will be erased. So basically, since capabilities get erased at runtime, the GC doesn't have a pointer to follow if we only allow a capability to be stored in memory, and then it gets erased. So we follow a very simple rule. Don't allow capabilities to be stored in the heap by themselves. They should always be paired with a pointer. That way, when the capability is erased, the pointer is still there. The garbage collector still can do its work. Yeah?
I have sort of the opposite question. So
yeah?
A pointer by itself doesn't have any ownership of anything at the other end.
Yes.
Mm-hmm. So how does the garbage collector know not to follow a pointer?
It doesn't have ownership. So this is the opposite question, which is that a pointer doesn't have ownership of anything that is actually pointing to. So how does the garbage collector know that that it should not follow it? The garbage collection is a very runtime concept. By the time we get to that stage, we've already done type checking of the full program, and we, assuming that you're not linking with any other code that didn't come from RichWasm, you have a safety guarantee. So that problem doesn't really arise. We erase the capabilities because we already know that everything that's happening is correct, in a sense. Okay, so just don't allow capabilities to be stored in the heap alone. Always package it up with a pointer if you're going to store it in memory. Okay, there are some additional things. I mentioned the roots of the garbage collector before. So the roots are our locations on the stack and they are unrestricted locations that might be referenced from linear memory. So remember I said we can have pointers from linear and pointers in both directions from these memories. But in particular, if you pay attention to the pointers from linear memory, they are our roots, right? Because you may not just have pointers from, roots that come from the program, you might have some pointers from here. So to avoid scanning the linear memory, looking for unrestricted locations, we assume that the runtime maintains an outset. So all of the pointers going from red to green here should be thought of as an outset. And they're just a set of linear locations that point to unrestricted memory. You can think of it as a pinned set, if you will, right? That's all we need to keep. Okay. Now, what if we have a pointer from unrestricted memory to linear memory, and then it might point to some other linear locations? A linear location can only have one pointer to it at any point in time. That means that this location is only pointed to from the unrestricted memory. There's nothing here that can point to it. So if the garbage collector comes along and collects this location, then it must also collect this and this and this, right? So it must follow those pointers and free the things in linear memory so that we don't have leaks. So we assume that the GC will recursively claim this chain of linear references starting from some location L. And to support this, now this is where we connect don't connect to the Wasm GC proposal. So in order to support this kind of pattern where we go and clean up, the garbage collector just goes and cleans up in linear memory as well, we basically need some notion of finalizers in order to implement that, which the GC proposal doesn't currently support. So that's a problem for us. Okay. How am I doing on time? As in, tell me what time it is.
It's not past.
Okay, great. Thank you. I didn't bring my phone. All right, so let's quickly go through an example just to give you a flavor of how this works. So here's a function. It abstracts over size sigma, which you'll notice can be has both upper bound and lower bound 64, so that says sigma must be 64. It abstracts over a pretype alpha that is upper bounded with the 64, and it abstracts over a location variable rho. All right? And what does the function do? Well, it takes as input a linear reference to a struct that has one field. It has a linear field. This is the size, so size 64. And then, by the time the function is done, it will basically take this value out of the struct field and return it. Okay? Well, you could have, I could have not, I wanted to show quantification over some kind of sigma. Otherwise, I could have just not done that and just put the 60. Oh, that actually should have been, I quantified over it because I'm trying to say that this struct has a certain size. Actually, I think maybe I should have made this sigma as well.
But you could not inline the 64?
I can inline it all. Yeah, this is just for the purpose of putting one more quantification up there, just to confuse you guys or illustrate more things. Illustrate all the crazy things that we can quantify over. Okay. I mean, this example is so trivial. The lower and upper bound are both 64, so you're absolutely right. Now, it can just be concrete. Okay. So that's the function body. Yeah, so basically what this code is going to do, and I'll step through it, is it'll extract the value stored in that struct and return it. So let's see. When we first call this function, what happens is that the argument to the function gets put into the locals of the function. All right, so that's what's happening over there. We have a pointer to some location where this struct will presumably be stored, and our locals support strong updates. That's why I have to put the 64 there, because I have to remember what is the size of this local. Because if I updated it, I can't put something bigger than 64 there. Okay, and what does ln point to? Well, it points to something in linear memory where my struct is sitting. Struct is of size 64, and it contains the number 42. Okay, now I'm going to do a get local 0, which means that I'm going to copy that reference to ln onto my execution stack. Okay. After that, I'm going to push unit onto the stack. So I just push that unit onto the stack. And now what we're going to do is a struct swap 0. Before I actually do that, let me explain what struct swap 0 expects. Struct swap 0 says, go find me a struct pointer, that's this guy, find me the 0th field of that pointer, and I'm going to put this value in there. That's what it's going to do. So let's go do it. So what it just did is it took the 42, put it on the stack, and it took the unit and put it in the struct. It swapped the 0th field of the struct. Do you want me to go back? I saw 2 confused looks. Right? It's like that. There's a 42 sitting in that struct. We're going to swap that with the unit. There. Okay? Then set local 0 is basically just going to set local 0 is going to put the 42 in there into the locals. And now we have this reference left to our structure, which we're going to deallocate because this is a linear thing and the function is not returning it, so we have to free it before the function returns. So go ahead and free the struct right there. And then to finish up, we're just going to do a get local 0 and copy that 42 from the local stack to the execution stack, and that's the result. Okay. All right. So jumping ahead, here's the shape of the typing judgment. So if you just ignore everything on this side of the turnstile for a second, this is basically a sequence of instructions that expects a bunch of tau1s on the stack and produces a bunch of tau2s on the stack. All right, but we keep track of so much additional stuff, right? Like there's all this kinds of polymorphism, there's stuff about memory, etc. That's why we need a lot of different environments. So let me just explain what's in the environments. Oh, I just realized we've actually changed the store typing to the letter S. I forgot to update the slide. But yes, store typing here keeps track of basically the types of data in unrestricted memory and the types of data in linear memory. And something to keep in mind is that as you type check subterms, you will have to split that sigma. You will have to make sure that you take disjoint parts of linear memory and give it to the subterms to type check, just like you would in any linear type system. Then there's the module context, which is pretty standard. It just keeps track of the, like WebAssembly, it keeps track of function types, globals, tables. F is the function context. We have polymorphism over a lot of different kinds of things, and F keeps track of polymorphic variables and the constraints on them. And then we have this context with locals. And again, because we support strong updates on locals, we're basically saying what are the types of the locals and what are the sizes of the slots. This sequence of instructions might do strong updates on the locals, so we have to thread the environment through and say, oh, what did you change the types to? Okay? All right. I'm just going to very quickly walk through one typing rule for struct swap. So we've already seen the struct swap instruction in the example. It's going to say, give me a reference on the stack to a struct which has a bunch of taus in it. It wants to go and update the ith tau, and it's going to update tau I in this struct with tau I prime. Okay? All right. So what happens after it's done the update? Well, it's a swap, so it takes the tau I and puts it on the stack where the tau I prime was. It takes the tau I prime and updates the type of the ith field in the struct. So straightforward, just like walking through it. There's the update. This instruction doesn't use anything in linear memory, so we make sure, it basically says that the linear part of S should be empty, since we're not using any resources. And then it says, ignore how it says it, but make sure that the new type, tau I prime, fits in the struct field so that its size is less than the size of the tau I, the ith field of that struct. That's why we keep the sizes of the structs. All right. Getting close to wrapping up. We proved type safety in Coq. It's a standard progress and preservation. A configuration which contains a store, the locals, and sequence of instructions can either, be a value, be a trap, or take a step. Preservation. Preservation says that if you have a well-typed configuration, then you can either take a normal instruction step or you can take a GC step. So again, this is why we axiomatize the GC. A GC step will, sort of conform to all the rules that a GC can and cannot do, right? Like how it can munge the state or not, and you'll still have something well typed. This was a Herculean effort. So I put lines of code up there. We still have a few substitution lemmas left, but even substitution is by and large mostly done. Okay, so just to wrap up, back to the example that I showed at the beginning. How do we, just a very, very simple flavor or sense of how we use this. So with this OCaml set of functions, basically our simple extension to OCaml in terms of the FFI is that we add this linear annotation on references. The OCaml type checker completely ignores this, this linear annotation, but what we use it for is essentially this FFI, tells the compiler, the ML compiler, that when you compile this down to RichWasm, you better annotate that reference with lin. So it'll end up being a linear reference, which means that then type checking at the RichWasm level will complain about this code. It'll say, oh, you're trying to stash a linear reference into an unrestricted cell. And therefore, type checking will fail at that point. And you can play with variants of this, but essentially type checking will fail at the RichWasm level if the wrong thing is happening. Right there. Okay, final slide. There's a whole bunch of different things that we'd like to do. Really the goal here is to develop a platform for interop between different type source languages. There are many, our focus so far has really been like what we thought of as a very hard case study, how do you get GSeed and manually managed memory to safely interoperate if you have kind of the safety assumptions at the source. But there, we don't deal with control effects, with many other things right now that we need to be able to handle. The first thing that we're tackling right now is actually extending this to Rust, because we can do ownership, but we can't do, in particular, immutable borrows. We don't know how to represent in the RichWasm type system yet. So how to represent immutable borrows, how to represent lifetime constraints. My student Sarah Marshall is actually working on that right now and has some very nice ideas. Then the RichWasm to Wasm compiler, right now we erase all of the type information in RichWasm when we compile down to WebAssembly, but we could use Wasm's custom sections to keep that information around and actually write a RichWasm type checker at the Wasm level. That would be like sort of akin to doing proof carrying code then. So the RichWasm platform is great for exploring all kinds of safe FFIs between typed languages right now. Right? The type system, we want it to be rich enough to be able to give you errors when you have type-safe languages interoperating. But you have to build the type-preserving compilers from those source languages. But what about interop with C code that was compiled to WebAssembly? We can't compile C code to RichWasm. The type annotations required would be, like, where are they going to come from? So ultimately, the thing that we'd like to be able to do is take typed languages, compile them to RichWasm, take untyped or unsafe languages, compile them to WebAssembly, but now you have the problem of safe interop between RichWasm and Wasm, right? And this is sort of an instance of gradual typing, but a little bit different. But of course, you have to do it in a performant way. So can you use, one of my students, Michelle, wants to look at, Michelle Talakoter, she's actually a co-author on this paper as well, wants to look at whether we can use static contract verification to avoid dynamic checks at the boundary. We won't be able to do it for everything, but can we minimize them? Another approach is to use something like compile to Cherry so that you can do capability checking dynamically. And then finally, we'd like to do a semantic model of RichWasm types as sets of Wasm terms. Such a model would allow us to prove correctness of optimizations in the compilation from RichWasm to Wasm. So the rest is, yeah. Okay, that's it.
So we have plenty of time for questions. I think we only have this mic, right? So I might need to go around and give it to you, so we hear the questions.
I have a kind of vague question. I'm not sure how to phrase. So my impression of RichWasm is you've added a lot of new abstractions, and they feel kind of like source level abstractions. You've sort of added new primitives to the language. Maybe that's necessary because you have new concepts you need to enforce. How do you enforce them if you don't know what the abstractions are? But that seems at odds with the goal of a low-level language, where you want a very small set of low-level primitives.
Yeah.
And what you would prefer is to sort of enforce a derived concept. So let me be concrete, you have struct axiomatized into your language. And it feels like what you're saying is, I know a priori what a struct is. It's a thing with a certain number of fields. It's a separate object from all other objects. But from a low-level perspective, you'd like to say a struct is an a posteriori, after the fact, I have this large chunk of memory. A struct is some subsection of memory that I want to treat as different, right? It's not a primitive concept, it's this derived concept.
Yeah.
That feels more like the low-level perspective where you have this high-level version of a struct.
Like in the proof-carrying code work from years ago, right?
Exactly.
We encoded structs using simply references.
Yeah, so I
individual
guess my
cells.
question is basically, have you thought about how you would do something like RichWasm, but from a more low-level perspective where you're deriving rather than axiomatizing more concepts,
So
or
I
whether
think-
that's possible?
Yeah, I think that we already are pretty low level. Like, we are not taking just source level things and building them in. The reason we built in struct and variant and array is because we were actually inspired by the GC proposal that was being worked on at the same time. Andreas had pretty much exactly those types, except not existentials, in the GC proposal, and so we decided to adopt them. But you're right, we could encode them. But the way in which we are low level is, we have these capabilities, and actually, even as we compile Rust in a type-preserving fashion down to RichWasm, our struggle has been, what are the lowest level concepts that we need at the WebAssembly-ish level, just only slightly higher than WebAssembly, at the WebAssembly-ish level, to encode these notions that might exist in high-level languages without baking in too strongly anything from any individual high-level language. So yeah, I'm very much a believer in the whole proof-carrying code concept in code, or typed assembly language concept, right? Find the most primitive building blocks that you can. It's just that, yeah, you're right, we didn't do this with struct and variant, and I think partly we were just sort of inspired by the GC proposal. We adopted them very early on. I think we could do it. I have to think through it a little bit more. I shouldn't promise it, but yeah.
Okay, a question here about sometimes your language would like to come with its own garbage collector. And that would mean that you would have to be able to express the garbage collector in RichWasm itself, right? Would that be is that possible? That's one question. And the other thing is, one of them might be a copying collector, right? And so then suddenly there will be other problems with borrowing and so on. So maybe you can comment a little bit.
So the way that I think about, I keep saying that so far we've axiomatized our garbage collector as far as the formalism is concerned, as in we haven't implemented one and verified it. And secondly, when we compile from RichWasm to Wasm, we have our own little simple naive collector. But the way that I always imagine doing this is, you pose a very good question. The way I always imagined doing this was that you would implement your GC and verify it. Then that way you can use some pretty sophisticated separation logic. You could use Iris or something to actually verify the GC implementation. Can we do GC implementations that would type check in RichWasm? That's a very good question. And to be honest, I haven't thought about it before. If I had to venture a guess, I think a simple collector might be okay, but anything more sophisticated, with subtle kinds of invariants that the type system can't express. Maybe the issue is, if you can write your type checker in Rust, then most likely yes. By the time we're done, at least with the Rust type preserving compiler, we'll be able to type check it. Assuming you're not using too much unsafe Rust. Right? So yeah. But thank you. That's a very interesting thing we should think about.
More questions, yeah.
I think the settings went to the screen. Is it not working?
Hi, thanks for the talk. You were talking about interoperability of two languages, and then you had these two different kinds of memory that sort of corresponded to the way memory was treated in those two languages. So I was wondering, if we want to have more general interoperability of a set of languages that could maybe be useful, would you need a different kind of memory for every single language, or do you think those two are enough to express anything that's plausibly useful?
I think those two. I think those two are enough to capture anything that's useful, because that's the fundamental divide, garbage collected versus not. If you do some sort of reference counted memory implementation, you can do that using the manually managed one. So everything can be mapped down. But yeah, these two ought to be sufficient.
Amal, you mentioned C, right, where you might have to go into gradual land, but like even ignoring that, how would that interoperate then in terms of memory?
How does that interoperate in terms of memory? Like if it's...
Like where would the C world memory live, right? That would be a third kind, wouldn't it?
I was thinking of C as... C would be manually managed, but it wouldn't be compiling to RichWasm, right?
Yeah.
So now we're looking at a world where we've compiled from RichWasm, like effectively we have the RichWasm types, but now you have C. I think the problem simply comes down to what are the RichWasm types, what are the constraints the RichWasm types are imposing on normal Wasm at that point? Oh, sorry. I think it simply boils down to an issue of RichWasm at that point having statically checked capabilities and normal Wasm coming from C having dynamically checked capabilities, or we need to dynamically check them if we want safe interop. So on the C side, you'd have implemented your own memory allocation and so on. So I think everything should be fine.
Right, but there would be a third kind of memory.
There would be a third kind of memory that's coming from Wasm this time, yes. Not in RichWasm, but outside, yes. Sorry, I didn't understand the question.
Well, it was kind of confused, but anyway.
Okay.
We have maybe time for one more quick question. Yeah.
Hello? Okay. Can you plug it in? So you did mention you must not have too much unsafe code in the Rust, right? Do you propose to annotate all unsafe code with this type system? How would it work?
The reason I said that, and it was just a throwaway comment, like it just suddenly popped into my head that what if you're using a lot of unsafe code to write your garbage collector? Here's the issue. Right now, we're talking about type-preserving compilation from Rust. And at least for starters, we're focusing on what type system features we need in RichWasm to capture the types of safe Rust, right? Unsafe code has, Ralph's done a ton of work on this, like unsafe code has different invariants. If we end up augmenting RichWasm with richer types than what you need for just safe Rust, then we'll be able to type check any, more unsafe code as well. How far do we want to go? And there's this trade-off, right, between type checking and verification. And I don't think we want to go all the way to the verification end and have like unbelievably sophisticated logics and have a crazy fancy type system. At that point, you just have a logic, not a type system, right? The reason we're trying to do a type system is because we're trying to give compiler writers a simple way of implementing safe interop. Like write a type preserving compiler, just do that, and then get some errors from RichWasm, right? It'll catch them for you. If we get too fancy, then the compiler writer's job becomes hard. So where's the sweet spot? I'm not sure.
Thank you.
Okay, I think we should move on. Let's thank Amal again.